See. Okay, I'm going to start. First, let me record it. Okay, so before I move to the agenda, at hand, I just want to spend a few moments. Okay, so just a few moments on this algorithm. I'll illustrate it on an example, and then I move to the main thing. So this is the main algorithm. So the first part in the then part in here, it starts with the usual BMC. Now you go up to K, and if you have not found any counterexample to K-long path, then you want to see if you have reached an inductive invariant. So that's when, so you have not found any errors up to some K. Then you compute the interpolant between I and for that K-safe interpolate. If that folds into I here, so it's the else part where you do the check to see if you have reached an inductive invariant. If you have, then you know that you have proved it safely. You can conclude that the property is verified. If not, you add the interpolant to the current initial state. And then you do this further BMC checking to see if you have, from that initial state, the enlarged initial state with the interpolant. So that is an over approximation to the actual initial state. Therefore, when you do further from K to say another K steps, if you get an error, that is if A and B is satisfiable, that is not a true error. So you can't conclude that it is a true error. Okay, so that's why that's why there is this check if Q is equal to S, Q is equal to S naught, since there can be some unreachable states in that thing. So in that case, what you can do is you can get out and you can increase the K, start from a bigger K and then take a bigger K, and then you can compute the you can restart the whole thing, and then you can do it for, choose to have a longer K, and then compute, restart the whole process. Okay, so that's what you do. So the most important thing to observe is that if the else part doesn't succeed in a full verification, then you would have increased the K, and you can continue with this thing. And if once again you get unsat for another K, then you go back into computing the interpolant and seeing if you if you have reached the fixed point. But if you do get a SAT, then what you'll have to do is you have to increase the K and restart from all over again, because that K was not, because there could be a bug which is more than K long, and that's how the loop works. Okay. So here is an example. Any questions there? Maybe you can, any questions here in the procedure itself? Okay. Yeah, this particular example is not a good example to illustrate the advantage of this method, interpolant method, over K induction, because actually K induction gets it in the same number of iterations. But nonetheless, it's a small example that can show how the thing works. So this is a transition system, and the states are encoded with two bits. There's only 4 states in the transition system. So the P1, P2 bits denote are used to encode the states. The initial state is one in which both P1 and P2 are true, that is S11. The only reachable states here are S11 and S10. Both S00 and S01 are not reachable. What I've shown here, the transition system I've shown as in CNF form, okay? as a conjunction of clauses. Each clause corresponds to one transition edge of the transition system. I've shown this in clausal form because how you extract an interpolant from an unsat proof from a resolution graph requires you to have a resolution proof, okay, which works on CNF form. But I'm not going to be showing that part today, okay? So, but nonetheless, that's the reason I have this in this CNF form. The property that I'm verifying is what, I mean, I've referred to as F, says it's V1 or not V2. So as you can see, this is a safe system since all reachable states satisfy this property V1 or not V2. Both S11 and S10 satisfies that. S01 is the only state, unreachable state, that does not satisfy. So if you were using K induction, is this property inductive, V1 or not V2, for this transition system? Anyone?
Yes, it is inductive.
Is it? Yeah, yeah. Is it? Okay. Why so?
If it holds at a state, it holds forever.
Yeah. Okay. So that is true. So even though S00, see, S01 is both S00 and S01 are don't. Wait a minute. No. S00 satisfies the property because it's not P2. Okay. But that's okay because, so it's actually one inductive. So whereas this property, I mean, the S01 state is kind of separated, and that's fine. So in one step, if you take, start with any property, I mean, the property itself is inductive because it separates those, the not P state. None of the P states or F states in this case, they no, contain any state that takes you out of an F state. So this is a good candidate for K induction. Okay, so BMC, a forward BMC will terminate in 2 steps. Okay, but you wouldn't know that unless you computed the threshold for this, the reoccurrence diameter. If you could compute that, then you could terminate after 2 iterations. In this case, you will see that you will require with the interpolant method also 2 iterations. It's not a perfect example for illustrating the advantage of iteration, but nonetheless, let's start. So suppose you start by doing, okay, 0, BMC 0, which means, sorry, BMC 1. So you take 1 step, P1, P2, and then take 1 step and then check if F is violated, okay? It's a safe system, this is not violated. You see the 1 step, yeah, okay. So now I want to see if I've reached the 1 step. Actually, in this case, also it gets it, but just checking. Yeah, in this case also it gets it in 1 step itself. I'm sorry, I made wrong statement. So what happens is, so now with this, since it's unsat, we'll try to compute an interpolant to check if it is If if you can get an interpolant that proves that it is that it is inductive. Okay, so the image here is the exact image of the initial state. Here is this one, P1 not P2, correct? Because that's the exact image. That's the only successor to P1, P2. That is P1 not P2. But an over approximation of that image, that is an interpolant, is something that also includes this state, okay, as 0, 0, correct? Because the bad state is not reachable from S00 either, okay? But that is not in the image. It's actually not even in the, as part of the reachable state. And therefore, if you compute an interpolant for this one, IP1, P2, BMC1 long formula with not of the property, you get this, okay? Now this resolution graph that I've shown here is how you compute the, extract the interpolant. I haven't explained that to you and I'm not going to, okay? So if there is interest, we can discuss this, later on. So, but for that, you need to know a little bit about resolution graphs, how you get a resolution proof, and so on. So now you have to check this whether, So now you take, you go one more step. So you combine this, the over approximation with the initial state. Okay, we'll take a union of the interpolant, which is not P2, with the initial state that you do ITP1, and that's what you do here. So that is equal to P1 or not P2. Since it is already, the property itself is, one inductive, then you go on to the second iteration. Okay, so because unfortunately this one is not, P1 or not P2 is not contained in the initial state, okay, which is P1 and P2. But if you go through one more iteration and then you do the extraction, okay, yeah, you include that in the initial state, okay, and then do once again one long BMC check. Then you extract. This is extraction of. So that's what I'm doing here. So I'm making the BMC formula with the enlarged initial state. Okay. Here. That's what I prime P1 P2 is. Then I'm computing the ITP, and that also is unsat here, okay? And therefore, I mean, when I do the BMC check with the enlarged initial state, it is still unsat. Therefore, that could be a candidate for an inductive invariant that we need to check by extracting an interpolant, okay, using the unsat proof, and that's what is shown here in the tree part. And what I get in the second stage ITP2 is P1 prime and not P2 prime. Okay. By the way, note this, because when you do when you construct the interpolant, it will be in terms of these primed variables. But before you take a union of the interpolant with the initial state, you will have to kind of move it into the 0 time frame, because the initial state, initial predicate will be a function, a Boolean function on the initial state. And that's what I'm doing here. So this, after moving to time 0 that you see here, is just replacing all the primed variables in the ITP, in the interpolant, and move them to time 0 before you take the union. Now, this one you see is the I union, the first ITP1 is contains ITP2. Okay. Correct. Yeah. So this is not exactly. I made a mistake here. ITP2 implies it's not ITP1, but rather I union. ITP1. That's what P1 or not P2 is, and that will give you a check that it is contained, and therefore, as you can see, P1 or not P2 is exactly identical to the original initial state plus ITP1, and therefore that indicates that you've reached the fixed point and the iteration concludes. So that's how this thing works. Okay. So any questions? Okay. So no questions. Then I will move on to. Okay. So the rest of the class, I'm going to devote half an hour to answering questions about CTL model checking, what questions you may have, and then I will talk about the next project and something that about using SAT solver, exploiting its incremental nature, which I want you to take advantage of in using the SAT solver for the second project. Okay, that's what I'll do. So what are your questions about the CTL MC? I thought some people yesterday said they wanted.
So I had a.
There's nothing, then I will move on. Okay. Are there any questions?
Hello. I have a question regarding the input that we give the program.
Okay.
So the input is supposed to be an SMT lib2 format, or I mean, how are we supposed to parse it?
It can be anything that's convenient for you now. We'll upload. Are you using Python?
Yeah. So right now, all I've got is like a set of functions, and the way
Yeah. So we can send you a parser. We can upload a parser to Moodle, which will let you.
Okay.
Parse formulas. But for now, just implement it however it's convenient.
So maybe it'd be good to explain when you give the parser, what does the parser do? So what is the input to the parser? What is the output?
I'll demo the parser on Thursday.
Okay.
Yeah.
I have a question regarding the counterexample generation.
Okay.
So
shall we answer? Okay. So why don't you? That's a technical question. So let me. Shoot.
Yeah. So
first of all, is counterexample generation necessary? Because I'm finding it unnecessarily complicated, sir.
No, I don't think so. You also, Kapil, you also said that just getting a transition relation for the microwave example was too complicated, okay? And I showed you how you get one, okay? So I don't think that was complicated. Okay, so if you have two choices, okay, so we have two choices. I think I'm going to go by whatever that was the problem that I made. Now you have a choice to submit without. This applies to everyone, not just to the person who's asking the question. So whatever that you have, you submit it, okay, today. And if you're having trouble implementing the counterexample generation, we will discuss that technically, okay? And then that will be graded separately, okay? Because we can give you a solution to your counterexample, then you can go ahead and implement it. So you have a choice, okay? Until Friday. I mean, you're free to do which way you want. If there's no one, if everyone is having trouble with implementing anything other than the CTL model checker, I mean, if on any part of the thing, then, well, then we'll have to, I have to help the entire class, okay? That's all I'm saying. But I will not entertain question, that's too difficult, don't assign me this, don't assign me that, okay? And which means that you can take over the class and you can give the assignment, okay? And that is not how it works. Now, if the entire class is finding it difficult, then I have no choice but to do. So maybe it is too complicated. I don't think so. And so I would. That is my expectation for you to do, for you to complete it. But if the entire class has no clue, it's finding it difficult, then I will discuss the entire solution and you can implement it, okay? And submit it, okay? So that's what I'm saying. So whatever state your assignment is in, we've decided that you should be submitting it today, okay? So we will take it on record that you submit. After that, threadbare, we will discuss the solution, okay? I mean, to some extent. We'll answer any technical questions.
Today is the deadline?
No, I told you that yesterday that it is, you have till Thursday to submit, okay? 2 more days.
Wait, so today we don't have to submit, right? I mean,
no.
Yeah.
I think I'm not making myself clear. So
I said, okay, fine.
I said whatever state it is in, submit it today, okay?
So then we can again submit later after.
No. Or what I will do is, okay, the reason that I'm asking you to submit it, because if some people have small questions about, clarifications about the thing. See, I can give you a solution to counterexample and how you implement. It's already described in the book for, to some extent, okay? But even if you don't understand, and then the idea is that you will have to apply your mind to something outside of what is completely covered in class. I mean, I even explained it to you. Maybe if what I explained was not clear, I'm willing to do it. So, but with whatever I've explained, I have to assume to some extent I have conveyed. And if some people have been able to get the counterexample, solution to that, then that's why I'm giving them an opportunity to submit a version today that has counterexample. Otherwise, we will discuss counterexamples. We have a small class, so I think we can do it informally. How many people are saying, but what I don't entertain question is, I don't want, so the assignment shall not have counterexample thing. Take it out. That kind of a diktat, I will not entertain. Please, you will have to pardon me for being, a bit harsh. So because then there'll be chaos. It'll be anarchy, okay? So everyone can be doing their own suggestion, making their own assignment, making whatever problems that they want, that thing. If you, as a group, say, oh, this is too difficult, none of us has been able to do it because either I have not done my part in explaining, then I'm willing to explain. If that is the case, then we will proceed. So I ask you a question, okay? So is everybody having difficulty in understanding how to go about doing counterexample generation? Not because, that is too hard, I don't want to do it, that is too difficult for the assignment. That's a different question, okay? So I want you to speak up.
I have a question about generating a counterexample for EU. So in class earlier, you said that you could do it with simply a while loop. So I have made a function that generates a counterexample for you, but it's like really complicated and not elegant. Is there like an elegant way of doing it? Because what I've done is like I've used BFS.
You see, I've already given you a clue. Okay, so this is something that I do. So we will go with the assumption that you all submit whatever that you have today, okay? A version. And then you will submit a version on Thursday, okay? So it seems like everybody, no one has implemented counterexample feature, nor, how about fairness? Has that been implemented yet or not? How many of you have implemented? How many of you are having problem even for that?
I've implemented both counterexample and fairness.
So you have implemented, you have to.
Yeah, mine is like my question is that my solution is not. It does not seem like
your name.
Argadeep.
Agdeep. Okay. Yeah.
So for you, my solution is really like looks complicated. It's like two different intermediate functions, and I was thinking whether there's a elegant way of finding it.
Yeah. I mean, I will discuss something, today. So yes, no, my question. Okay, so you have implemented both, but you think that the way that you're doing may not be elegant. Does it seem to work?
Yeah, I think it works.
Okay, good. So yeah, so that I don't want to shortchange, people that have put in the effort to do it. Okay, I mean, with the thing. Therefore, I want the people who have done it, whatever form it is in, you submit it. That's why I'm saying everybody submit a version that you have, and then I'll explain all the technical questions, for the thing, short of giving you a complete implementation, and then you submit another version. Okay, this is all. It's not the end of the world. I mean, finally, the purpose of any course and any of these things is for people to understand. Okay, for all of us. And if there are issues that I somehow overlooked, it is for me to take that learning experience as well. Okay, so there's no ego, here at play. So who else? So before I start discussing the counterexample generation, so I asked the question: how many of you have been able to do the basic CTL? I guess all of you have done. So fairness, how many of you are having problems with that? Anybody? Okay, so I'll assume that implementation is fine. So it's the counterexample that is probably, other than Argadeep, other people are having trouble. Is that fair to say? Well, maybe I should address Somadev.
Yes, sir. I just implemented till fairness. I didn't.
Good. Okay, Diganta, you want to have some technical question answered. Kapil, you're having, you have not implemented either. Okay, so let me start by discussing, so what I, at a high level, say, okay? So if this is the overall thing. If it doesn't work, this method, then we can discuss, okay? So what I have is, you have to save. The general idea is to save in each iteration that you compute. On the way to computing the fixed point, you save the intermediate BDDs. Look, you first complete the, so you save the BDD in each iteration. You reach a fixed point. Then, so while you compute the fixed point, you save the BDDs. This could be a naive approach. There could be other approaches which may be more efficient, but this is a simple approach. So you save all the BDDs, okay? And then it's only after you compute the fixed point that you can check whether the transition system, whether the property is violated or not, correct? By checking if the initial state is inside the fixed point. Now, if at that point it is completely inside, there's no, the property is verified, there is no need to generate the fixed, counter example. If not, then I'm saying generally, if it is like safety property, okay, where the counter example is finite, is a finite path. So, like for example, AG of P, okay, of some formula, okay. Then you have to find a path from S0 to some state that is violating the P. So I'm taking the example of AG of P, okay? So since you've already saved all the BDDs along the way, what you have to do is you have to pick a state from that satisfies an initial state in the BDD that of the fixed point that you generate. From there, you go to the the next BDD that you have saved. Now here there is some variation. Sometimes you compute it backwards, sometimes you compute it forwards. Okay, so what I'm claiming is that you should be able to express it by extracting a state from that first BDD and then going to a successor state that is contained in the next BDD and so on. Okay. Does that help you? Now you can ask your question. Okay. There is one additional thing. This is for safety. Violation of a safety property always has a finite path. Okay. So you will have to, if you've saved all the BDDs along the way, then you should be able to get to something in which not of P holds good. So here I'm assuming that
something like strongly connected component not necessary here.
No. That is for yes. For those things, strongly connected component is not necessary. Okay. If it's a liveness property, okay, suppose it's AF of P. In all these cases, since P itself can be another CTL formula, I'm assuming that you already computed the counter example for that. Okay, so at that level, whether it is AF of P, if it's AG of P like property, then it is a safety property. If it is AF of P, then it is a liveness property. Then you will have the counter example has to end up in a strongly connected component. Okay. Now, it is the second bullet here that tells you how you could do that. You will have to get to a state. And how do you check if, is something that you have reached a strongly connected component? So for safety properties, it is clear. I mean, I hope it's reasonably clear, correct? When the counter example is a finite path.
I did not understand. I tried to understand, sir, but I could not.
Okay, so what is it that you did not understand? Yeah.
How exactly if storing the BDDs help there? I could not understand.
So let's
find a path, right? So we take an initial state and then we have to take its neighbor and something like that.
Correct. Yeah.
So if we take any state in the BDD, that might not be the neighbor, right? Am I missing something?
No. What you will have to do is you have to, in all the state that you have accumulated, you have to first take an initial state. So because when it is violated, there is an initial state that is not contained there, correct?
Yes.
Yeah.
By the way, are you sharing screen? No, right?
Oh yeah, I'm not. I am sharing. I intended to. So sorry because I gave it up. Oh, shoot. Okay. Oh, I've been talking without sharing a screen. So how do I? So I've been blabbering all the while without sharing screen. Okay, same, when it violates, suppose you're doing an AGP, okay? You do an AGP and then you know how to compute the fixed point for AGP, correct? And then you check if your initial state, initial predicate is included in that. Suppose you say it's it is not, okay? That means there exists a state from the initial state that leads to a not P. So you run that. So there must be, okay, there is an initial state that is not included. So what you do is you run EF of not P, okay? Argdeep. So here you can jump in, okay? So if the method that you're using is different. So what I'm saying is, suppose you want to generate, you have checked AG of P, that you have concluded is not verified. What does that mean? That means that some initial state was not included in the fixed point, correct?
Yeah.
Okay. I mean, the rest of you who don't have will have to answer. Okay. So is that how I'm assuming you're checking whether the model, whether the property is verified or not, correct?
So yeah. So for AG, I'm doing EF
I
of not.
especially want others who don't have. Okay, no, it's good that you have. Okay. So Diganta, Kapil, are you with me?
Yeah.
How about Kapil?
Yes, sir.
Okay. So now, so you know that there is an initial state, okay, which is not, which violates it. So what you have to do, you have to now get from one of those initial states, you have to demonstrate that there must be an EF of eventually where you reach not P, correct? So you run the EF of not P, which is the negation of AG of P. That will be true. Okay? So it is there that you save all your intermediate BDDs. That will get you, if you traced from an initial state and the next BDD, you will, you have to extract a BDD from the next one that is reachable from the from the one that satisfies the first BDD and so on until you hit a not P. Okay. Existence of EF of not P is where you will have to now generate a fixed point for that. I mean, it's as though you are now, because you know that EF of not P will hold good. And therefore, every, and if you save all the BDDs during that thing, and then you extract a path from the saved BDD while verifying EF of not of P, okay? Am I making
How
sense?
exactly do you find the path?
Well, no. First, I want to make sure that because you also said that you didn't understand what use is saving all the BDDs. Okay, so you understood this two distinction, right? So the counterexample generation will have to be generated from the saved BDD of a proof of EF of not of P. Is that point clear?
Yes. We have to generate the BDDs for EF of not P.
During that is also a fixed point computation, okay? So during that, if you generate it, now, so there is this question. Now, then you have, with the saved BDD, you know that there is, what do you do? So when you do an EF of not P, you first you have a BDD that satisfies not P. To that, you add some states which may or may not satisfy not P, which is usually satisfies P, but that gets into a not P. That is the next thing that you compute in your fixed point, okay? The next iteration of fixed point. You save that. Then you add to that those that go to not P in 2 steps. That is what your EF of not P is doing. So all the way until it terminates with a initial state.
So for checking EF, we start with a BDD that contains everything, every states, right? That represents
Not every state, not P. Not every state. It contains every state.
The greatest fixed point, right?
No, when you do EF of not P, you are adding things, okay? It's only for EG that you're using greatest fixed points. But a similar argument holds good there also. So I'm explaining.
Yeah, EF we are doing the least fixed point. Sorry. Yeah.
Yeah.
So fixed point.
So you're starting with not P. Then you will have a BDD which contains all states, okay, that in one step lead to a not P. Then you have, in the next iteration, you have state.
But least fixed point, we start with false, right?
What?
For least, we are generating the least fixed point, right?
Correct. You start with not P, not false. You start with those states which satisfy not P.
Sir, in the algorithm given, we are starting with false, right, sir? Could you check?
No. Not false. What do you mean false? False is empty set.
Empty set. Yes, we are starting with empty set and moving towards a least fixed point, right? We apply tau repeatedly.
No. The fixed point, you start with false, correct. But the very next time that you apply tau of 1, you get not P, okay?
Yeah, exactly. Okay. Okay.
So that you save, not P. And from tau 2, you get, those states that are reached to a not P in 2 steps. Tau 2 will get in 1 step because tau 0 is false. I understand. Okay.
Okay. Got it. I'm getting it, Samara. Now I'm getting it.
Yeah. So that is the idea. okay? So, because witness to an AG of P, a witness to an AG of P, a violation of AG of P is actually a witness to EF.
So, but we find a state which satisfies not P. So from that state, how do we go to initial state? There might be many paths.
No. That's why where does the initial state come? All the way until the very end. Okay.
Fixed point.
And that is when you reach the fixed point, there you can actually check. Okay, there are so many interesting and smart things, clever things that you can actually do.
Okay.
Think about it.
Go backwards.
Actually, you can do. You don't even have to wait until you get all the way to the fixed point, because if not P itself is one of the initial states, bang, you're done. Okay.
Okay. So we go to initial state at the end, very end of the fixed point, and work.
Once again, you're asking the same question. That is one thing that you can do. You can compute EF, fixed point of EF of not P all the way, and then do, but you can do better than that. I'm actually explaining that, okay? So at each step, you can check if indeed, at each step in the iteration, as you are doing the iteration for a fixed point iteration, you check first, when do you start? Tau 0 is false, tau 1 has not P. Suppose that itself has an initial state, okay? Then you have found a counterexample of length 1. I'm saying that is, you can, so you can then give a witness, okay? If that does not have not P, then you will compute one more iteration in the fixed point, which will give you all the states that start from P that goes into not P. Then you will check if those states, before you actually add that to add that to not P, the tau 0. I'm saying tau 0 is false, tau 1 is not P, tau 2 is something that you will tau 2 will actually union it. But before you do that, if you can compute that image, then you can even check if that contains, even after tau 2, if that contains the initial state, from there now you will have to take that one of the initial state and then take the state, its successor state. That is a state that is in tau 1 and also is related by T. That's how you do. So then if indeed, okay, then you will get the minimal counterexample. If you wait until you get the fixed point for EF of not of P, then what you have to do is pick a state in EF. Then you would have saved all the BDDs all the way to the fixed point. Then you have to start unwinding from S naught. Okay, what I just now described just a while ago was a more optimized version. Where?
So could you repeat the optimized version? Sorry, but could you?
Well, I'll have to. Do other people get it or not? Guys, you have to be more responsive, okay? So, tau, where did you, you have to either stop me right in the beginning, okay? So I'll repeat once more, okay? So first, I'll ask question and then I want you to answer, okay? Because I'm screaming here, and if I don't get any answer, either you turn your, let's all turn the video on, okay? And maybe that is the best way to do, okay, so that I can see your faces. I'm going to turn my video on, so I'll explain again. Is none of what I've said is clear? Not even 1% of it, or is some of it clear? If not, what it is. I mean, you will have to tell me that, so that if you can stop me where I'm not making sense to you, then I don't need to keep repeating, okay? So, do you all agree that witness to a violation of AGP can be extracted from a proof of EF of not P? Yes or no, please?
Yes.
Yeah.
Others? I'm not hearing.
Yes.
Yes, sir.
Diganta?
Yeah.
Okay. So the question is, how do you extract that? Okay. How do you compute EF of not of P, the fixed point? What does, okay, so like Kapil pointed out, you start tau 0 is always false. What is tau 1? That is the first step that you do.
Not
It
P.
will be not of P, correct? Yes?
Yeah.
Okay, so you save that. Now, what I'm saying is, check if I is already intersects with that. If you luck out, if it already intersects, you take the intersection of I and not P, get a state from it. That is a counterexample. Is it clear? Or are you still in doubt? If you take the intersection of I and not P, and if that is not false, you have a counterexample, correct? Why? Because your initial state itself is satisfying not P. Isn't that a counterexample for AG of P?
Yeah.
What is it that you didn't understand, Kapil?
So in the end,
Now you have, what that means is you have a counterexample of length 1.
yes, sir.
Maybe I intersection not P, which is tau 1, is false. Then you do tau 2. Okay? Do the same thing. So if tau 2 happens to intersect with I, then you know that you have a counterexample path of length 2. There, what you have to do is take something at the intersection of I and tau 2. And from there, you have to take a state that satisfies tau 1, that is not P, and such that the two are linked with T. So now, once again, that constraint can be expressed as a BDD. At least that part you will have to think and how to do it. So conceptually, what I'm saying is, if tau 2 intersects with I, then you know that that has a state which in one step gets you to tau naught, a tau 1, which is not P. So you have to extract from I intersection tau 1, that is your first state in the path. And then you will have to do tau 1, tau, so you tau 1, tau, you have to get the successor state of that, okay? Of something which is in the intersection of I and tau 2. So so that you will do I intersection tau 2 and T, and T of the so you have to express the constraint that it is contained in the tau 1, and the two are actually related by your transition relation. And if you constructed the BDD for that, then you will have you can extract the successor. Essentially, you have to extract the successor state for I intersection tau 2. Okay, which is so that is where you have to think a little bit. Okay, how you will do that. You already have tau 1, you already have tau 2. You know that tau 2 intersection, suppose tau 2 intersects with I. So you have to now pick among those, you have to pick among the states that satisfy tau 2, something which is, so you will have to kind of compute the pre-image, okay, from tau 2 to tau 1 such that it is also intersects with I, okay. That is the BD that you will have to, that pre-image, okay. You can compute, and then that will give you something that is in I that will get you to the successor state, okay. Now I can work out the details and lay out the solution to it, okay. I can do that. Did you at least understand it conceptually? That so there is some details as to how you will exactly implement what I've said in BDD, okay? We can give you help even for that, okay? I mean, to the extent that we will work out, so if you're not able to do it, you're not able to do it, okay? What can you do? I mean, I'll say that, it was too tough of a problem for 90% of the people, then I'll have to confess and move on. But so I ask once again the question is what you have to do, how you might implement in that BDD may not be completely clear. Those details I'll have to, I can, Zubin and I can work out and then give it to you, and then maybe you can implement it. But at least conceptually, is that clear? Each one of you, please answer yes or no.
Sir,
Because
it's clear, but I had a question.
No. First, I want to answer from all the rest of the people.
So this is clear.
It is clear to me.
Yeah. To me as well.
So, but let's see, there's some chat question. Oh, Samudev is answering yes. Okay. Is Samudev even here? Yeah. So I think, then the question is, how do you construct a BDD? But it is one way is, that is where you have to think a little bit. So you know that there is things. So at each step, maybe you will have to construct a image, or what you do is the moment you have all the BDDs, the moment you see at some tau I step, it intersects with an initial state, then you can start computing the forward successor. So you have to figure out how is it that I can compute a successor of a state that intersects I, that is in I intersection tau I, and goes to tau I minus 1, okay? And then, so that is like you're computing the image, okay? You compute you can either compute the entire image, pick one state from that, or you could just, I think that is the way that you will have to do. You will have to express the post image as a BDD, take a satisfying assignment from that. That you have to repeat until you hit not of P, because you won't know which one to pick until you know. So you have to come all the way to some tau I, that during that computation, so you can, instead of waiting till you reach the fixed point, you can actually check if it is if it intersects with I at any tau I, and then you pick one initial state from I intersection tau I. Then you compute all its successor by computing the post image. Okay, from between that and the of I intersection tau I, you will get that, and so then you pick that, and then you compute the post image of the state that you have picked from tau I minus 1, compute the post image, and so on until you hit a not P. Okay, so that's what you will have to do. So here's what I do. So since we are so this is something I wish we had. Maybe I'll take some, because either I know Kapil was the one that was saying that he was not able to do much earlier on, and maybe we should have had this discussion early on. Not too late. We have had the discussion. At least for AG of P, you do, okay, that I've described. For one other operator, you do it. I'll be happy, okay? So that is what I want you to. I want you to do. Shall we agree to at least you will attempt that, so that you will get to know? Huh?
Okay, sir. Sir, also, sir.
Go ahead. Yeah, before I do that, I want let me answer your question, and then I'll go to Argdeep, because he said that he had some solution that I want
to extend the deadline to at least Saturday, sir.
No, I'm okay. You see, I'm very okay with that. Okay, so you can take till next Tuesday if you want. Okay.
Okay. Thank you.
But the idea is that you should try and implement it. I think this is, the details of how you extract with the post image, etc., that I was hoping that you will be able to figure out yourself. Now, the thing that I mentioned, maybe I did not, if I did not, the thing is, you guys, I wish you ask more questions in the class when I do something which is not fully explained. I know, one thing that I wish that you did was interrupted me and then said, no, I don't understand. And I guess not much of that is happening, which is somewhat disappointing to me. And then, it's only when we hit these kinds of things that I do. So now I don't completely blame yourself. I'm of the thing that, the teachers are the ones that you do. But there's also this thing of here where you explain certain things and then you have to expect, the students to think a little bit more and then maybe do it. Otherwise, I can only give questions that doesn't let you think too much, okay? Maybe this problem was too much to think given what I had indicated. If that is what you guys think, I'll take the blame for that, okay? But at least, we can agree that it is, that you understand now, and hopefully that you can implement it. Okay, Argdeep, so you had something.
So in my solution,
how had you implemented it?
I did for EU. What I did was I treated the transition system as a graph, and then given an initial state, I performed a BFS using the EX relation.
That's also, so what you did was, okay, maybe, that's, so, but the thing is, okay, that's a solution, yes. But, that kind of, so it's not a symbolic, the counterexample is not via symbolic model checking. So you did the symbolic model checking part, you did
I did that separate
part using symbolic model checking,
Yeah.
And you ended up constructing the transition system in a graph. And
No,
this is-
I didn't actually do it in a graph. Like I just treated it as a graph, and I used the EX function that I already had, the EX counter example. I used that as a transition relation,
okay.
and I had to define like adjacency and other functions. That's why it is so. I mean, it's big.
You had to introduce other functions means what? Which-
For adjacency, like so I'm only considering the part of the transition system that satisfies, say, EU of F and G. If I'm checking a counterexample for, I mean, a witness for EU of F and G.
By the way, see, the way I have defined counter examples, this is a, maybe you can say it's a subtle point, but it is, see, the way counter example is defined is for a G-like property or AF-like property, it is a real counter example. It's a negation. You want a witness to the negation, which is a E operator.
Yeah.
But if the property that you're verifying is an E operator, then witness to that itself is a counterexample.
Yeah, that's what I have found.
That is, you can't just take the negation of that.
Yeah, I found a witness to that.
EU. So what I just now explained is pretty much EU. I mean,
yeah. So so I've done a sort of, I mean,
but for EU, showing a witness for EU doesn't require you to do strongly connected component at all.
No, I didn't do that.
Huh?
No, I basically eliminated all the vertices that does not satisfy E of FUG.
But were you representing your graph as how? How were you representing your graph? As a formula or how?
Well, it is just how it already was. Like it's a BDD, and the transition relation is EX of.
So you must have done something similar to that, okay? So you did it for EU. You were generating a witness for EU, correct?
Yeah.
So there's no, for EU, there's no question of strongly connected component, because how would you generate? But you did it in a forward direction?
Yes, I did it in a forward direction.
Okay. No, you could do it in a forward direction also. So then you would do, you will compute the post image, correct? So yeah, there exists a state that goes to the next one. That you can do too, but you will not get the shortest one in that case. That's all.
No, with BFS we will get the shortest one, right?
Huh?
Because we're doing BFS.
But no. That depends though. I mean,
yeah, actually, maybe, yeah.
If in each step of doing EX, if you're checking if the next one is a P, which in our case is not P here. Okay, so if you're doing that, then you will get. Okay, that's also another way. That is, you can, The only, So this is also doable. I guess what you're doing is then it will give you. See, the breadth-first search itself gives you shortest, but when you do the entire computation, okay, fixed point computation, you have all the states from the initial state, okay, that reach a P state in one or more steps, okay, correct?
Yeah.
But how do you pick the shortest one among them? That is what I mean, a short witness to be, because if you did it in the forward direction, you could still do it, but you will have to do that extra check. Oh, I'm starting from some initial state. I'm computing the post image. Oh, is that in P already? Okay, is my initial state already in P? Then I can pick it. Then is my post image in P? Then I can pick it. Okay, that way you can do as well.
Yeah, that's what I've done, I think.
Okay. So that's also another solution, guys. Did you understand what Argdeep has done? See, what I did was I was starting from tau 1 and then doing it, okay? And then I was doing the same thing of post image. But what he's doing is he's doing at the very end, okay? When you do that at the very end, then maybe you don't need to save these BDDs, do you?
No. So I just add the previous state. So I have encoded state in like a tuple, and then I just add it to the path.
Okay. Yeah. So you don't need to save the BDD. Yeah.
No.
Yes. So yeah. Maybe this is even a better method. Okay. So if without saving BDDs, what you're saying is you compute the fixed budget. Yeah. If I get it, okay, the rest of you should also kind of understand. So you are computing it all the way, and then you're starting. Okay. So full fixed point you're doing for EFFP, and you're starting with the start state,
Yeah.
but then at each
Then I'm
step,
computing all the adjacent states that also follow EF of P.
yeah. No. But when you do that, you have to ensure that you've already hit the P. Okay. In one step itself, you might have hit P. Okay.
Oh yeah. I check whether I've hit the P. If I have, I stop computation right there. If I haven't, then I check the next.
Yeah, that you can do too. Yes. So this might even be. This will not require storing the BDDs either. Yeah, but you will preempt. But you will have to compute the full fixed point. Okay, that is the drawback here, because you have to first compute EF of P and then do forward chaining. Correct?
Yeah.
Okay. Yeah, this is also not bad, because it has the advantage that you don't need to save the BDDs. Did the rest of you get what Ardeep was doing? Hello?
Yes, sir.
Yeah, so I guess you can do that thing as well. So you have done BDDs, okay? I'm sorry, your implementation is in terms of BDD. The only the other thing that I want to mention, so it's already 4:45. I don't think we'll get to discussing the team project at all. Hey guys, I had told you. I mean, I know that it's not entirely to you, so I'm not going to blame you for that. So I want, at least for you to make an attempt. I've already sent the message to all the people to be present as a full team to listen to my description of the project. But if that is not going to happen and people don't show up, then I will, just do this project description in the next class, and whoever shows up, or I may not even do the project discussion. I will just post it on Moodle, and if you have questions, you can ask me. Okay, but one thing is, send me by email whoever your teammate is, and you have to make sure we're all grown-up adults. So you will have to make sure that your teammate does pull in his weight. And if that is not the case, unless you bring it to my attention, I'm not going to get in to solve that problem for you. Okay, that is something that I've always done. If in the then I'll assume both of you have done equal weight. Now, if indeed you want to pull your weight for your teammate, that is your prerogative. Okay, that is one. So I will post the project description. I was going to discuss it, and there were a couple of things that I wanted to discuss in terms of incremental SAT. For which it is too late now, because the other one, the other discussion got everything. We can do that next time as well. So those are some tips with the implementation and how you do the input, etc. But whoever shows up, I will describe, and whoever doesn't show up, it's for them to listen to the thing. Okay. So, but I do make a request. Just send me an email as to who your teammates are, because I can't keep that in my mind. Yeah.
So I have just one slight technical question regarding
Yeah.
the counterexample. So if you have a nested formula, is the counterexample going to include counterexamples for subformulae and so on?
Yeah, I think the simplest way to do is the following. I don't know, maybe there are more optimized way. I haven't thought about it. But the following is acceptable for me. So if you do, even for two things, if you do it is okay with me. Okay, one of the EF kind, one of the G kind. Okay, so you first generate the formula for the nested one, and you just concatenate it. Now, won't that work?
Yeah, so basically a proof for the sub-formula failing or holding, and then a proof for the
Yeah.
outer formula failing or holding based on that or something.
Correct. Yeah.
Okay. Yeah.
Yeah, I'll be happy if you could do even for one level. Okay, that, and if it's just concatenation would do. But whether there are shorter counterexamples than just concatenating is something that I have not thought through. So shall we agree that you will submit it by next Tuesday and you will try to do this? Yeah, and you should start thinking about.
I have another question.
Yeah.
If, suppose we have a formula like EF of P. So is the witness supposed to only have a path up to the state, but it does not satisfy? I mean, it satisfies EF of P, or is it supposed to like
First
find?
of all, EF of P. You can
Actually, I don't know, like some similar nested formula.
No, EF of P reduces to EF of P, correct?
Then it's probably like equivalent to EF of P. But suppose it's like
The EF is,
AG AF of EF of P, or
those kinds of things. Yeah.
yes. So are we supposed to find a path that leads up to a state that satisfies or does not satisfy EF of P, or are we supposed to provide a path from the that state showing that it leads up to a path that does not satisfy P? So like are we supposed to find one level counterexamples of it all the way down?
No, this counterexample should take the negation of this whole thing. Okay.
Yeah. So AF of EF of P, then it's
So
negation of EG of negation of EF.
EF of AG of not of P. That's what
Yeah.
you'll find a witness.
Yeah.
So I'm talking about finding witness to EF of AG of not of P. Okay.
Yeah.
So assuming that you have a witness for AG of not of P, okay, which you've already done.
No, I mean, in my implementation, it does not do that. So since I have a function witness EG of a BDD, so AF of P is just a BDD. So it finds a path to a state such that it satisfies only the outermost.
Yeah, no, what I'm saying is that that's the question that Diganta also asked, okay? So I know what you have done is you only do for EF of one level, okay? Of not of, I mean, you're not doing it for nested thing, correct? Yeah. What you do is you get a state in which AG of not of P is satisfied, and you find a counterexample from the initial state to EF of that state, correct?
Yes.
Yeah. Now I think we can decide, because we are, and since you have to get started on the next project as well, as long as, since all you need to do is concatenation, if you're doing it, then as long as you have a general procedure which for doing AEF, AG, and doing AG of finding a witness to, this gives a new question. Okay, so what you have done is you've found What you have done is, okay, so let's assume, since I'm eager to get started for the class as a whole, one level, for all the CTL operators, okay, one level counterexample is good enough, okay, for the purpose of this assignment. Yeah, let's agree on that pact. Is that fine?
Yeah.
That's what you have done, you said, correct?
Yes.
Yeah. So that, as far as my evaluation is concerned, I'll be happy with that. So let's agree on that. But going back to this question, Diganta, okay? Diganta's question. Now, when you do a negation, the inner one will become AG of not P, correct?
Yeah. So I mean, for those we can't have a witness. So I guess we'll just have to print out that such and such formula holds it in such place, and that's all we can do.
Yeah, that's a good question. Yes. So.
Also, it is fine if we do it only for AG and EF, right?
No. But I'm saying, since you're not doing for nested one, do it for U and R as well. Okay. For one level thing. Because U and R are somewhat similar. Yeah. At least for U, you can do EF, EG. This one I need to think. Yeah. So let's discuss, think about this, at least conceptually. So as far as assignment is concerned, one level is fine. Okay. So AG of, so this one maybe needs a reformulation. It's a good question as to how witness is generated for these kinds of things. For the purpose of our thing, since we agreed to one thing, but still as a class, I would like us to get illuminated on this. Can you test it on a new SMV and see what it does? Okay. For nested CTL operators, what kind of counterexample it gives? Does it give path counterexample all the way down? Does it even make sense? Okay, that's something that I'll have to think about. It's a good question. Okay, so this discussion is turning out to be illuminating. Yes, I'm glad we did it. So is it clear? So I will send out the next project on this thing, and we'll have some discussion. Try to encourage your teammates to show up, or you discuss with your teammates separately. Yeah. Okay, guys. Yeah. I know that I raised my voice today a little, more than the thing. So don't take it too personally with anyone. Okay. So just take it in the right spirit. Okay. Okay. I'll see you on Thursday.